Welcome to the Crazy Hat Chemist. So here we go with another video here and a pen and pencil, if you will, example of gas laws. So which video are we doing? We are doing the behavior of gases worksheet number 2. So make sure that you have watched worksheet number 1 and the worked out solutions therein. And this is going to be worked out solutions number 2. So before we get started on this, a few things that you need to keep in mind. Number one, you need to have your nomenclature known. That's your chemical nomenclature. You also need to have your chemical reactions unit known, and also you need to have your stoichiometry unit known. And if you have any doubts on those, then you should probably take a look at my videos on all of that information on YouTube, The Crazy Hat Chemist. So, the next thing that we're going to make an assumption with here is that you know some of the equations in which we'll be using here today. So right here, this is the combined or general gas law right here, PV over T equals PV over T. That's the general or combined gas law. A derivation of that would be Charles' law, where the pressure is held constant with Charles' law, and that's V over T equals V over T. A derivation of the combined gas law is the Gay-Lussac's law, and that is where the volume is held constant. So that's P over T equals P over T. And then a derivation of the general or combined gas law, where the temperature is held constant, is Boyle's law, and that's PV equals PV. And you can see that there's a condition 1 and a condition 2. Condition 1, condition 2, condition 1, condition 2, condition 1, condition 2 with each one of those. So effectively, the general or combined gas law can get you Charles' law, Gay-Lussac's law, and Boyle's law if you were to hold the pressure, the volume, or the temperature constant. Another law that we need to know is Dalton's law of partial pressures. That is, the total pressure is equal to the sum of the individual pressures of gases, okay? And that is each gas has a pressure that's independent of each other, and that's why you can sum them up. The next one is Avogadro's law, and that's a relationship with volume and the amount of gas, where the amount of gas does not change. We'll talk about that later. There's the ideal gas law, and that is not a comparison, and that's PV equals nRT. Then R is the gas constant, by the way. Then there's Graham's law, and Graham's law is comparing how much faster or how much slower one gas is compared to another one. And that's an inverse relationship, square root inverse relationship of either the molar mass or the density of the gases. That is, at the same temperature, the gas will, a low molar mass gas will move faster than a high molar mass gas. Then we actually have a derivation of the ideal gas law, and that is density of gases, and that's PM over RT. And how you remember this one really simply is density equals Phil Mompriond, that's my name, Phil Mompriond, the Crazy Hat Chemist, Phil Mompriond, is a Rio teacher. That's perfect. So hopefully don't forget that. Then another thing that we're going to need to know is that at STP conditions here are 273.15 Kelvin and 100 kilopascals. This number 100 kilopascals has been since 1982. Some textbooks still use 1 atmosphere as STP conditions. That's incorrect, but if your textbook uses that, then you can use that. At STP, 1 mole of any gas is equal to 22.414 liters, and hopefully you are familiar with that. That should have been something you're familiar with in the stoichiometry unit. Additionally, you need to know your pressure conversions, and these are the ones that we're going to be using, although there are many other pressure conversions, but in this unit here, 1 atmosphere equals 760 millimeters of mercury equals 760 torr equals 101.325 kilopascals equals 1.013 bar, okay? The other thing that you need to know is we are going to be using this particular periodic table right here. It's the periodic table from the SAT subject test. So hopefully you're familiar with that one, and that's the one that we're going to be using for calculating all our molar masses. All right, so without further ado, let's keep on going here and see what we got. Hold on just a moment. All right, so we're going to continue here, and we're going to start off with our first problem here, the behavior of gases worksheet number 2. I just gave you a brief summary of the gas laws in which we might be using here. All right, so let's give this first problem a try. It says a gas occupies a flask at 75 milliliters and 1.52 bar. So this milliliters lets us know that this is a volume. The 1.52 bar, that is a pressure. And these two things go together here. We'll call this condition 1 and this condition 1. Okay, it says, what is the pressure? So that is pressure 2. I don't know that. I'm solving for that. If the flask's volume increases to 0.085 liters. Those liters let us know that that is actually the other volume 2. Okay, there's no mention here in this problem about temperature. Therefore, the temperature is going to remain constant. Okay, so what we are actually using is we are using the combined or general gas law, and I'll write that down here. P1 V1 over T1 is equal to P2 V2 over T2. And then since temperature is not mentioned in this problem, that means it's going to be constant. So I'm going to scratch that out. And what I have is Boyle's law. So this is an example of Boyle's law. And one of the things that you should probably know is that you should probably be familiar with and aware of what laws have what part constant. That is, Boyle's law has temperature constant. All right. So then the next thing that we need to do is make sure that all the units are in the same set of units here. Now I'm solving for pressure, so I'm going to keep this pressure in bar, and my ending pressure will be in bar. Okay. But my volume, one of them is in milliliters and one of them is in liters. So I need to convert either the milliliters into liters or the liters into milliliters. And it really doesn't matter. It's entirely up to you which one you decide to do. I'm going to make the arbitrary decision of converting the liters into milliliters. So I'm going to start off with 0.085 liters, and then we are going to convert this into milliliters. So this is just a single one-step conversion here from liters to milliliters. So let's take a look at this. You should be aware of this. This is 1 liter is equal to 1,000 milliliters. Okay, the liters cancels out and I'm left with milliliters, and so that will be 85 milliliters. I'm maintaining the number of significant figures here. This has 2 significant figures. This has an infinite because this is a definition, and this has infinite because it's a definition. So therefore, this is 85 milliliters. All right, so I have 75 milliliters at 1.52 bar. So I'm going to place those into this equation here. So I have 1.52 bar and times the volume, and that's 75 mils. And that's going to equal my second pressure, pressure 2, and then I have now my 85 milliliters, just like that. Okay, and simply I'm going to solve for P2. So I'm going to divide both sides by 85 milliliters here, like this, 85 milliliters. Okay, you should see that this cancels out entirely. This is a multiplication division problem, so I'm looking at significant figures in order to determine my ending significant figures. The milliliters will cancel out. This number has 3 significant figures. This number has 2 significant figures. This number has 2 significant figures. So my ending result of pressure 2 is going to have the fewest number of significant figures of which are in these 3 numbers, which is 2. So the answer here is 1.52 times 75 divided by 85, and that will equal 1.3 bar. And then that is my answer. So hopefully that works out well for you and you're comfortable with that number there and those set of units. Okay, if it told me what the gas was, then I would put that gas, whatever that gas is in there, but it doesn't actually give me what the gas is, so I don't have to worry about that. All right, fantastic. Let's move on to question number 2. So let's push this up here and check out question number 2. All right, so question number 2, it says you have a container of gas at 69.5 milliliters. That is a volume. Okay, and we'll call that volume 1. And then it says we have 642 millimeters of mercury. That is a pressure. I'll call that pressure 1. And then 37.3 degrees Celsius. That is a temperature. I'll call that temperature 1. Then it says, what is the volume? So that's going to be volume 2. That's a question mark. If the conditions are changed to 103 kilopascals, that is a pressure. Kilopascals lets us know it's a pressure. And then we have at 56.8 degrees Celsius, that's temperature 2. Okay, so I am actually using the units to determine what this is. So milliliters gives me volume, millimeters of mercury gives me pressure, degrees Celsius gives me temperature. It says what's the volume. The volume will be in the same units that are here, which are milliliters. And then kilopascals is a pressure and degrees Celsius is a temperature. Okay. One of the things that you need to know is that you have to, for all gas law problems, and I didn't mention this when I went over the equations themselves, but all gas law problems, you must use units of Kelvin for every single temperature. That's absolutely a must. So you must maintain temperature or convert all temperatures into Kelvin. That's just, you have to do that. This problem here has volume, pressure, and temperature, and I'm solving for a volume, and there's another pressure and a temperature. So this is actually using the general or the combined gas law. So let's write that down here, okay? And so that's going to be P1 V1 over T1 is equal to P2 V2 over T2. So I'm actually plugging into the combined or general gas law. Now, the other thing that I need to do is I need to make sure that all my units are in the same correct units that are necessary. That is, this temperature right here needs to be converted to Kelvin. That's necessary. This temperature here needs to be converted to Kelvin. That is necessary. And then my pressures need to be in the same set of units. And I'm just going to make an, you have 2 choices here. You actually have 3. You can convert the millimeters of mercury into kilopascals or the kilopascals into millimeters of mercury. Those are the 2 most obvious, easy choices. Alternatively, you can convert the millimeters of mercury into some set of units, maybe bar, and the kilopascals into some set of units. They must be the same, bar. So that would be the long route. We're not going to do that one. What we're going to do is we're going to convert the kilopascals into millimeters of mercury. That's going to be the easiest one. So I'm going to say 103 kilopascals. And then we're going to use the unit conversion, converting kilopascals into millimeters of mercury. That's real simple here. Let's do this one-step conversion. This is 101.325 kilopascals. That's equal to 760 millimeters of mercury. Okay, and then what we're going to notice here, oops, kilopascals. Let's write that all in there. You notice that the kilopascals units cancels out. This has 3 significant figures. This has an infinite number, and this has an infinite number because both of these are equal to each other. These are definitions. So what we're going to do is we're going to end up by taking 103 times 760 divided by 101.325, and I'm going to get 3 significant figures of 773 millimeters of mercury. Now that is going to be pressure number 2. That is that number converted into millimeters of mercury. All right. So now what we're going to do is we're going to convert the temperatures into the correct set of units, which is going to be Kelvin. So that's our next step. Okay. So now what we're going to do is we're going to convert our 2 temperatures into Kelvin. All right. And that's a simple method of here is the equation, and that is Kelvin is equal to degrees Celsius plus 273.15. That is what we're doing for all our temperature conversions from degrees Celsius to Kelvin or Kelvin to degrees Celsius, but we will always in this unit be converting to Kelvin. So what we're going to do is do both of our Kelvin temperatures and get what we need to. So that is going to be 37.3 degrees Celsius plus 273.15. I'm going to maintain the fewest number of decimal places, which is 1. And so that will be 310.5 Kelvin. There's no degree symbol on the Kelvin. And then I have 56.8 degrees Celsius plus 273.15. That's going to equal 330.0 Kelvin. That's also to 1 decimal place. So both of these have to 1 decimal place. All right. Now we're going to do, by the way, this is the first temperature. So this is called temperature 1. This is temperature 2. So just make sure that you keep those in line. Now, what we're going to do is we're going to plug directly into this combined or general gas law with everything that we have now. We've converted all our units as is appropriate. So let's just plug on in. So the first pressure number 1 is 642 millimeters of mercury, 642 millimeters of mercury. And then we have a volume, and that is 69.5 milliliters. And then we have a corresponding temperature. This is going to be temperature number 1. And that is going to be 310.5, 310.5 and Kelvin. Then we have the other side of this, and that is the condition number 2. So we do have our new pressure that the 103 kilopascals has been converted into millimeters of mercury. So this is 773 millimeters of mercury. And we are actually solving for volume number 2. So I'm going to just say V2 for that right there. And let's have a nice drawing right here. And then we're going to have temperature number 2. That's 330.0 Kelvin. All right, now we're going to make sure that our units cancel out. Our units of Kelvin temperatures, our units of millimeters of mercury, and the units that don't cancel out are milliliters. We're going to look at significant figures here because this is multiplication division. 642, that's 3 significant figures. 69.5, 3 significant figures. 310.5, that's 4 significant figures. 773 millimeters of mercury, that's 3 significant figures. And 330.0, that's 4 significant figures. So the fewest number of significant figures I have on this is 3. So what we're going to do is we are going to, in our calculator, we're going to do the following. Mathematically, it's cross multiply, right? That's probably the easiest way, and that's what probably most students do. So how are you going to do this in your calculator? 642 times 69.5 times 330.0 divided by 310.5 divided by 773. And then I'm going to get volume number 2, and that's going to have 3 significant figures. That's going to be 61.3 milliliters. And that's going to be your final answer to 3 significant figures. Okay. Hopefully you like that. That looks good to me. Let's move on to the next problem, and that would be problem number 3. So let's push this off to the side here, and let's take a look at problem number 3. Here is problem number 3 right here. All right, so problem number 3, let's check this out and see what we've got. Okay, it says if a gas fills a 16 mil container, that 16 milliliters, the milliliters lets me know this is a volume. Okay, and 18.6 degrees Celsius, that's a temperature. That's volume 1, temperature 1, and torr, 257 torr, that is going to be a pressure. Okay, we're going to calculate the volume in milliliters, and this is in milliliters, so that will be nice and easy if the conditions are changed to STP conditions. So what are STP conditions? And I had mentioned this at the very, very beginning here, and standard temperature is 273.15 Kelvin. Standard pressure is 100 kilopascals. Okay. All right. So what we're going to do is we are going to, first of all, we're going to make sure all our conversions are correct. So we're going to make sure that all our temperatures are in Kelvin. So we need to convert this degrees Celsius into Kelvin. The other thing that we're going to do, since this is 100 kilopascals, and so that is a definition, so that's going to be an infinite number of significant figures, and this is going to be an infinite number of significant figures, since at STP that those are the defined values. So those are both infinite number of significant figures. I need to convert this pressure into kilopascals. So I'm going to do two conversions here, one from degrees Celsius to Kelvin and one from torr to kilopascals. So that's what I'm going to do right now. So I'm going to say 257 torr. And I'm going to convert this into kilopascals. So again, all the pressure units, all the pressure conversions are one-step conversions, really simple one-step conversions here. So this is torr. That means that this needs to be torr down here. This will be 760. That's torr. And then 101.325 kilopascals. You should see that the torrs cancel out. This is infinite, and this is three significant figures. So I'm going to maintain three significant figures, and that will be 257 times 101.325 divided by 760. That's going to equal 34.3 kilopascals. So that's my pressure number one. Now I need to convert my temperature. That's 18.6 degrees Celsius. I need to add 273.15, and now I will have my new temperature, and that's going to have one decimal place on this here. Okay, because this has one decimal place, that will have one decimal place. So we're going to have 291 point, I think that's 8 Kelvin. All right. So this is actually a combined or general gas law problem here. Okay, which is, I'll write this down. P1 V1 over T1 equals P2 V2 over T2. So a general or combined gas law problem. We are actually solving for the volume. That's volume number 2. So we're going to plug right into this equation here. So our pressure at condition number 1 is 34.3 kilopascals. And our volume at condition number 1 is 16 milliliters. And our temperature at condition number 1 is 291.8 Kelvin. And then we have condition 2, which is at STP conditions, So the pressure is going to be 100 kilopascals. That's a defined value. We are solving for volume number 2, and our temperature is 273.15 Kelvin. That's also a defined value. So we're solving for the volume. This has an infinite number of significant figures, because they are at STP defined conditions. This has 2 significant figures, this has 4 significant figures, and this has 3 significant figures. So effectively what we're doing is we're doing the same thing that we did on the previous problem, and that is crisscross applesauce, cross multiply, in other words. So here's what we're going to do in our calculator, and that will be 34.3 times 16 times 273.15 divided by 291.8 divided by 100, and I'm going to solve for V2. And that's going to have 2 significant figures here, and that's going to be 5.1 milliliters. All right. Hopefully that looks really good for you. Remember STP conditions, and some of you who have different textbooks and maybe different instructors might actually have used 1 atmosphere instead of the 100 kilopascals. So you're just going to have to work with whatever your instructor tells you. All right, so that's problem number 3. Let's move on to problem number 4. Oh, by the way, a quick little advertisement here for myself. I am the Crazy Hat Chemist, and please watch my YouTube videos. You can look up the Crazy Hat Chemist and you can see my YouTube videos. I would appreciate you giving me a thumbs up on the video. I would appreciate also if you subscribe to my YouTube channel, that would be greatly appreciated. All right, so number 4. Let's see if we can pound out number 4 here. Number 4 isn't so bad. It's a complicated problem because it says something that I'm going to highlight here in just a second. So we have 34.5 milliliters. That is a volume. It says the gas is collected over water, and I'm going to highlight the portion that says over water. When it says over water in the problem, that effectively means that I'm going to be using Dalton's law. And that's Dalton's law of partial pressure. So that's going to be very important. In a iodometer gas measuring tube in a lab where the temperature is recorded to be, okay, we have a temperature. Notice that that's in degrees Celsius. We're going to have to convert that to Kelvin. And a room pressure of right here, that's the pressure, says the vapor pressure of water at the same temperature is found in the CRC, Handbook of Chemistry and Physics, to be 23.196 torr. And what is the volume of the dry gas at STP conditions? Okay, so this is a complicated problem, and this is a fantastic free response question on a test here. All right, so this problem here is P1 V1 over T1 equals P2 V2 over T2. Okay, so one of these conditions is going to be wet. One of these conditions is going to be dry. So we're going to call this the wet conditions, and we're going to call this the dry conditions. What are the dry conditions? Dry conditions are at STP. So just like on the previous problem, number 3, standard temperature is 273.15 Kelvin. The standard pressure is 100 kilopascals, and we are solving for V2. Okay, so we do have our dry conditions. These are defined values because they are at STP. Now we need to get our other temperature, and that is this 24.6. Notice it's happening twice in this problem. And we have our other volume, that's the 34.5. But what we have to do is acquire this pressure right here. And it says that the gas is collected over water. That means that we have to use Dalton's law to acquire this pressure. That means the pressure is actually not given of the wet gas. Okay, so that's the first thing that we're going to do. Okay, and so we're going to take a look at Dalton's law. The total pressure is going to equal to the partial pressure of the gas plus the partial pressure of water. So this is Dalton's law. The total pressure is equal to the sum of the individual pressures. And since this gas is collected over water, then one of the gases is water vapor. And this value, the water vapor, is always a tabled value from a table. And that's why it's the CRC Handbook of Chemistry and Physics. That's this value right there. Then the other pressure here is the total pressure. That's this one right there. Okay, but I need to have them in the same set of units. So what I'm going to do is I am going to convert this 23.196 torr. I'm going to convert this into millimeters of mercury. Now, some of you might actually be able to do this in your head. I certainly can, and I'm certain that you can too, but I'm just going to show you what it looks like. So if you remember, the very first thing that I talked about on this was 760 torr, one of the equations, and also the pressures, and 760 millimeters of mercury. So you should see that whatever the torr value is, it's the same as the millimeters of mercury. So this is going to be 23.196 millimeters of mercury. So it's actually the same numeric value. All right, so fantastic. All right, so what we're going to do is plug directly into this. And the measured value from the room pressure, which is measured on a barometer, hopefully most commonly, that is going to be the 774.5 millimeters of mercury. I'm going to solve for the pressure of the wet gas that is collected over water, plus the partial pressure of the water, 23.196 millimeters of mercury. All right, this is a simple problem here. What we're going to do is subtract 23.196 from both sides. When we are subtracting, we're using the fewest number of decimal places. This number has 1, this has 3 decimal places. So I'm going to end up with the partial pressure of the wet gas with 1 decimal place. Okay, and so that will be 751.3 millimeters of mercury. All right, so now I have the pressure using Dalton's law, okay? And I've been given the volume, that's 34.5, and now I need to convert my temperature. So my temperature is the 24.6. So let's convert that. So we have 24.6 degrees Celsius. We're going to add 273.15 to this, and we're going to get 298. Sorry. Let's try that again. 297.8 Kelvin. I'm using the fewest number of decimal places, which is 1. All right. So now what we're going to do is we are going to plug right directly into this right here, which is the combined or general gas law. Remember, one condition is STP, so that is the pressure of 100 kilopascals and the temperature of 273.15. I just converted this other temperature here, that's temperature 1. I now have the pressure of the wet gas that goes right here. And I have the volume of the wet gas, that's the 34.5. I'm going to plug all that in, and then I'm going to solve for the volume of the dry gas. So I'm going to plug all these values in. I'm going to move this up just a little bit so that you can see plugging into this equation right here. And let's see what we got here. So moving this up, I have, let's see here. Oh, I need to do one more thing here before I actually do this. So hold the boat, hold the boat. So one more thing that we need to do is, since this is a defined value at STP, and this is in kilopascals, I actually need to convert this millimeters of mercury into kilopascals. So let's do that. 751.3 millimeters of mercury. I'm going to convert that into kilopascals. So here we go. Again, I'm always going to that defined value. And so this is 760 millimeters of mercury, and that is 101.325 kilopascals. And so that is going to equal 100.2 kilopascals. And that's rounded to 1 decimal place right there. Okay. Now we have all our parts. Now we're going to be plugging into the combined or general gas law. All right, so I'm going to move this up, and let's see what we got here. So we have our 100.2 kilopascals that we just solved for. That was our pressure of the wet gas. The volume of the wet gas is 34.5 milliliters. And the temperature of the wet gas is 297.8 Kelvin. Now, this is going to equal the dry gas conditions, and that's 100 kilopascals at STP. We're solving for V2. And the temperature at STP conditions is 273.15 Kelvin. So we're going to solve for V2, and this is very similar to what we have done before. That's cross multiply, solving for V2. I'm looking at significant figures. This has 4 significant figures. This has 3 significant figures. This has 4 significant figures, an infinite and an infinite. So the fewest number of significant figures I have on this problem is 3. Plugging this into our calculator, we're going to take 100.2 times 34.5 times 273.15 divided by 297.8 divided by 100. Volume 2, to round it to 3 significant figures, is 31.7 milliliters. That is our answer. All right. That was problem number 4. What I'm going to do is just kind of zoom out on this and make sure that you can see this whole entire problem here so that you see all the different parts of it. Okay, so again, just as a quick little summary, when it says over water, you are absolutely using Dalton's law. This is Dalton's law of partial pressures. You are going to be given the partial pressure of the water vapor that's at a specific temperature. It must be the same temperature as what's occurring in the rest of this experiment. The total pressure is the measured pressure of the room, the barometric pressure, the atmospheric pressure. That's what this is. Says that we're going to get the volume of the dry gas at STP conditions. Remember, those are defined values with infinite number of significant figures, 100 kilopascals, 273.15. We're going to solve for the partial pressure of the gas. That's what we've done right here. We're going to convert that into kilopascals because our STP conditions are also in kilopascals. And our temperatures need to be in Kelvin, so we're going to convert our degrees Celsius into Kelvin. And then we're using the combined or general gas law, and we're using significant figures, right? Cross multiply. Hopefully that's not too bad. All right. So now what we're going to do is we're going to cruise on into the next problem here. Just a quick little advertisement break here. Please watch my videos. I am the Crazy Hat Chemist. Watch my videos on YouTube. Please subscribe to my YouTube channel. Pass it on to your aunts, your uncles, your cousins. Ask them to subscribe. If you have any friends in other countries, ask them to subscribe. I'm looking for new subscribers. And give me a thumbs up. Thumbs up. All right. Here we go. We're going to tackle problem number 5. Let's see what we can do here. Says if 3.5 milliliters of hydrochloric acid at a density of 1.18 grams per mil reacts with an excess amount of zinc metal, what volume in liters of gas is produced at STP conditions? So this is actually a stoichiometry problem, and you should have been able to solve this with the stoichiometry unit, but that's okay. No worries. Let's give it a try here as well. So zinc, that's a solid. It reacts with an excess amount of hydrochloric acid. That's HCl. That's 8Q. This is a single displacement reaction. The zinc is going to displace the hydrogen. You will have hydrogen gas that is diatomic. Plus zinc chloride. Zinc has a 2+ charge. Chloride has a 1- charge. This is going to be aqueous. Then what we need to do is balance this. There's going to be a stoichiometric coefficient of a 2 in front of the hydrochloric acid. Like I said, this is a flat-out stoichiometry problem, so let's see if we can hammer through this problem here with our stoichiometry. We're going to start off with 3.5 milliliters of the hydrochloric acid. The milliliters needs to go down here of the HCl, and we're going to use the density of the hydrochloric acid, 1.18 grams of HCl over 1 milliliter of HCl. Okay, that will enable us to cancel out the milliliters of HCl. All right, I should keep this ruler handy here. Grams are over here, therefore grams needs to go down here, and this is going to be the molar mass of hydrochloric acid. That is 36.461 grams of HCl, and that's equal to 1 mole of HCl. And here we go. So that enables us to cancel out grams of HCl. Now I'm going to cancel out the moles of HCl. So moles of HCl need to go down here in the denominator. I'm going to go to moles of whatever it is that I want. And it says that I'm going to go, what is the volume in liters of the gas produced? This is the gas, so I'm going to go to the hydrogen, and that's the gas. So the stoichiometric coefficients in front of the hydrochloric acid is a 2, and in front of the hydrogen is a 1. And there we go. This enables us again to cancel out moles of HCl. 1 mole of HCl, sorry, 1 mole of H2 is equal to 22.414 liters of H2. And that occurs only at STP. This enables me to cancel out the moles of H2. This is a multiplication division problem, so I got 2 significant figures here. This has 3 significant figures. This is an infinite because there was no number there, so we had to place a 1. This is infinite. This is 5 significant figures. Infinite and infinite for my stoichiometric coefficients. Infinite, and we'll call this 5 significant figures. So the fewest number of significant figures I have on this is 2. Fewest number of significant figures. So what were we going to do in our calculator? We're going to plug into the calculator the following numbers: 3.5 times 1.18 divided by 36.46 divided by 2 times 22.414. We're going to round that to 2 significant figures. That will be 1.3. The units are liters. The formula is H2, and there we go. Number, units, formula with the correct number of significant figures. Bam! Fantastic. That is number 5. We got number 5 nailed down perfectly well. All right. Let's pound on through number 6 and see what we can get for number 6. All right. So cruising this all the way up here like that. There we go. All right, number 6, it says, which gas is slower and by how much by comparing krypton with butane at the same temperature? So what's key on this problem is that it's at the same temperature. If it's not at the same temperature, I'm going to have to use something different than what I'm doing here right now, but this is going to be a Graham's law problem. Okay, so the first thing that we actually need to do is acquire the molar masses of these gases. So krypton is smack dab on our periodic table. That's right here at 83.80. So 83.80 grams per mole of krypton. Butane, we're going to have to calculate that. We're going to take carbon, that's 12.011. times 4 plus 1.0079 times 10 and round that to the fewest number of decimal places, which hydrogen has 4 decimal places, carbon has 3, so this will be rounded to 3 decimal places. So this will be 58.123. That's kind of nice. 123 grams per mole of C4H10. Okay. And so now what we're going to do is we're going to compare these 2 numbers. Okay. We're going to figure out which gas is slower. The slower gas has the greater mass. So which gas is the slowest gas? Well, the slowest gas is the one with the bigger mass or the biggest density, and krypton has the larger mass, so it has the largest density. So that means that we are going to be using krypton is the slowest gas. Okay, does that make sense? Hopefully that makes sense, right? Okay, so krypton is the slower gas. So that answers one of our questions. Which gas is slower? Krypton. Boom, answer right there. Now we're going to figure out how much slower krypton is compared to butane. That is using Graham's law at the same temperature. Graham's law says the following information here. Rate of krypton over the rate of the butane is equal to the square root of an inverse relationship. So that means that the butane's molar mass is going to go here, 58.123 grams per mole, C4H10. And then krypton's molar mass is going to go here at 83.80 grams per mole of krypton. So what we're going to do is we're going to plug these two numbers here into our calculator. Notice that we don't actually need to put this. The units of grams per mole cancels out. So this number that we get in our calculator, rate of krypton over the rate of butane, we're going to get a number in our calculator, and that number is going to be the following. That's going to be 0.8328. I've rounded that to, this has 5 significant figures, this has 4 significant figures, this has 4 significant figures, leading zeros don't count. When I get a number that is less than 1, when I plug into this here, that's 58.123 divided by 83.80, square root of that, and I get 0.8321. When I get a number that is less than 1, that tells me that that gas is slower. And then what's the denominator of this? That is 1. All right, so hopefully that makes sense. So which gas is slower? Krypton. I'm going to get that number by comparing the two molar masses. The one that is larger in terms of molar mass is the slower gas. And then plugging into Graham's law, I get how much slower. So krypton is 0.8328 times slower than butane. Look, if butane was traveling at a rate of 1, then krypton would be traveling at a rate of 0.8328. Just for giggles, okay, if you wanted to figure out which gas is faster, then your answer would be butane. How much faster is butane than krypton? And that would be rate of butane over the rate of krypton. And so that is effectively the inverse of this. So if you have this in your calculator already, you can take the reciprocal or the inverse of this value. And what you will get is 1.201. Again, what's the denominator? 1. When you plug this into your calculator and you get a number that's greater than 1, that tells you that that gas is faster. So butane is 1.201 times faster than krypton. Butane would be traveling at a rate of 1.201. Krypton would be traveling at a rate of 1. Okay, that's number 6. So hopefully you are happy with number 6. I answered which gas is slower and by how much, krypton. And I also answered another question which was not asked, but just in case, which gas is faster, butane, and by how much. So I got both of those in there. All right. Little station advertisement. Remember, I am the Crazy Hat Chemist, and please watch my videos on YouTube. You're probably watching this one on YouTube. Please subscribe. And hey, you know, if you like cooking, then check out some of my cooking videos as well. I got some good cooking videos up there and more to come pretty soon. So check those out. All right, let's see if we can answer some more questions here on gases. And our next one here is number 7. So number 7 is we are going to calculate the density in grams per liter of trinitrogen hexoxide at 0.845 bar and 56.4 degrees Celsius. All right. So what we're going to do is we need to first get the formula of trinitrogen hexoxide. Okay, so so it's nitrogen oxide, and it's tri and hex. So you need to know your prefix naming. That's a binary non-metal compound that is a gas. All right, we're going to calculate the density. All right, and so density is equal to my name, Phil Montbriand, and my profession is I am a teacher. And what school do I teach at? Rio Americano High School in Sacramento, California. All right. There we go. So Phil Mombriand is a Rio teacher. This is density is equal to the pressure times the molar mass divided by the gas constant divided by the temperature. Okay, so what we're going to do is say density is equal to, and we're going to come up with what this is equal to. All right, so the first thing that we are going to do is we are going to plug in the value of R. The R is the gas constant, and that is 0.0821. And it has 4 units associated with it. Those units are liters, atmospheres, moles, Kelvin. Okay, so the reason that I plug in the gas constant first is that it tells me what the units are for the pressure, the temperature, and for the molar mass. Okay, so that is absolutely essential. All right, just like on any gas problem, the temperature must be in Kelvin, as noted right here in the gas constant. So the first thing I'm going to do is convert this 56.4 into Kelvin. So I'm going to add 273.15 to that. I'm going to round that to 1 decimal place. Okay, and then I'm going to get the following value. That's going to be 329.6 Kelvin. That will enable me to cancel out the units of Kelvin, right? Then the next thing that we're going to do is we're going to do a pressure conversion. And so we're going to take this pressure here of 0.845 bar, and we are going to convert that into atmospheres. So it is to do this is 1.013 bar, and that's equal to 1 ATM. Okay, and this has an infinite number of significant figures, because both of those are definitions. Leading zeros don't count, and this has 3 significant figures. So this answer here with 3 significant figures, I'm going to say 0.845 times 1 divided by 1.013. And I'm going to get 0.834 ATM. Notice that the number really has not changed a whole lot, but it has changed just a little bit, because you should see that this is 1 and that's 1.013. The numbers are very, very similar, very, very close to each other. Then the next thing that we're going to do is we're going to pull out our periodic table, and we're going to calculate the molar mass. That's the M portion of this, the molar mass of trinitrogen hexoxide. So that is 3 times 14.007 plus 6 times 16.00. I'm going to round to 2 decimal places. And that value is going to be 138.02 grams per mole of N3O6. All right, so let's make sure that all our units cancel as is appropriate. So you should see that the moles cancels out. Then the atmospheres cancels out. What does not cancels out is in the numerator, I'm going to have grams. In the denominator, I'm going to have liters. And a mass per unit volume, that is a density. So I'm going to plug this into my calculator. I got 0.834 times 138.02 divided by 0.0821 divided by 329.6. This has 3 significant figures. This has 5 significant figures. This has like either 3 or infinite. It's kind of like a definition, so you could call it infinite here in this particular case, and this has 4 significant figures. So the fewest number of significant figures I have is 3. So I'm going to plug this all into my calculator, just like I mentioned there to you, and this is going to equal 4.25. That's 3 significant figures, grams per liter of N3O6. And that is the density of trinitrogen hexoxide at these set of conditions right here. All right. That is number 7. And so let's keep on going. And we got one more problem down here on this this page here before we move on to the next page. All right, fantastic. So here we go. Number 8. Scroll this on up. And here we go. Number 8. It says determine the volume in liters of 0.39 grams of nitrogen. What's the formula for nitrogen? Well, the formula for nitrogen is N2 because it's diatomic. If the following conditions apply, 115 kilopascals, that's a pressure, and 13 degrees Celsius, that's a temperature. So I'm going to ask myself, do I have 2 of anything? So one of the complications here is, do I have 2 of anything? I do not have 2 of anything. So since I don't have 2 of anything, that means that I am not using the combined gas law, general gas law. I'm not using other gas laws of Boyle's, Charles, or Gay-Lussac's. I'm not determining how much faster or how much slower one gas is compared to the other. So what I'm using is the ideal gas law, just like I'm the ideal teacher of chemistry. Oh, that's a joke. Okay, here we go. PV equals nRT. This is the ideal gas law. And what am I solving for? Volume. So that means I'm going to rearrange this and divide both sides by pressure, and that will solve us for volume. So I am going to solve this for volume. So volume is equal to nRT over P. All right. So what I'm going to do is I'm going to first kind of set this up and plug into this here a little bit. Volume is equal to, and we'll draw our line here. And the first thing that we do is we're going to plug in the gas constant, that is the R, very similar to what I did on the previous problem. And that is 0.0821 liters, atmospheres, moles, Kelvin. All right. The reason I plug in the value for R is that R has specific units, and I need to make sure that those units are the same units that are with all the other portions of this. Okay, that is, the pressure must be in atmospheres. Is the pressure in atmospheres? No, it is not. So I need to convert this pressure into ATM. The temperature must be in Kelvin. Is the temperature in Kelvin? No, I need to convert it to Kelvin. And then this N, in order for this to work out and cancel out Kelvin and the pressure, so the temperature of Kelvin and the atmospheres here of pressure, and in order for me to solve for a volume and the units that do not cancel out is liters, I need to cancel out the moles. Therefore, the N is the amount of gas, and that must be in moles, so I need to do that. So I'm going to do my little conversions here at the bottom here. Okay, so I'm going to start off with 0.39 grams of nitrogen, and I'm going to convert this into moles of nitrogen. So I'm going to look at my periodic table, say 14.007 times 2 because it's diatomic, and therefore I'm going to get 28.014 grams of N2. That's equal to 1 mole of N2. You should see that our units of grams of nitrogen cancels out. This is really one-step simple stoichiometry. This has 2 significant figures, infinite, and then 5. So I'm going to have 2 significant figures. I'm going to plug this into my calculator, 0.39 times 1 divided by 28.014, and I'm going to get 1.4 times 10 to the negative 2 moles of N2. So I'm going to plug that right into this here. 1.4 times 10 to the negative 2 moles. And that is N2. So you should see that the moles will cancel out. So I should be good to go there on that. Another unit conversion I need to do is I need to convert my temperature into the proper units and the pressure. So we'll do the temperature first, and that is 13 degrees Celsius here right at the bottom of the screen, plus 273.15 That's going to equal, with no decimal places, rounded in the ones column, 286 Kelvin. So my temperature is 286 Kelvin, just like that. And that will enable me to cancel out the units of Kelvin right there. Got one more unit conversion to do, and that is 115 kilopascals. And I am going to convert this into atmospheres, 1 ATM and 101.325 KPA. And this has three significant figures, infinite and infinite, because these are both definitions. So this number here is 115 times 1 divided by 101.325. And I'm going to get 1.13 ATM. That's rounded to three significant figures as what was originally in the 115. My atmospheres will cancel out. Now, what does not cancel out is liters. And what am I asked to solve for? A volume. Oh my gosh, no way. That is super cool. All right. So now what we're going to do is we're going to look at significant figures. This is two significant figures. We'll call this infinite here. This is three significant figures, and this is three significant figures here. So the fewest number of significant figures I have is 2. I'm going to plug this into my calculator in the following way. 1.4 times 10 to the negative 2 times 0.0821 times 286 divided by 1.13. And I'm going to round this to two significant figures. That will be 0.29. The units are liters. The formula is N2. Hidden zeros don't count. So I have 0.29 liters of nitrogen gas. Boom! That is the correct answer for that. Hopefully that works out well for you. I'm looking at that and I'm liking that, and that's a great problem. This is using the ideal gas law here. You could also have this in exponential notation with two significant figures, and that would be 2.9 times 10 to the negative 1 units of liters, and the formula of N2. Remember, nitrogen is diatomic. Don't forget that. All right, let's see here. Quick little advertisement break. I try to do this as every time I come down here to the bottom of my page, and that is, please watch my videos on YouTube. I am the Crazy Hat Chemist. So there we go. All right, I think we have one more problem to do on this entire setup here, and that's right here. And let's see if we can hammer out some of this here in just a bit. So we're going to read through this problem here first. It says calculate the mass in grams of 0.34 liters. That's a volume. Sample of CH2Cl2. That gives me a formula. From that formula, I should be able to obtain the molar mass. At 692 millimeters of mercury, that is a pressure. 79.4 degrees Celsius, that's a temperature. So the question is, do I have two of anything? Do I have two volumes, two pressures, two temperatures? And the answer is no, I do not have two of anything. Consequently, I am going to be using the ideal gas law. So that is PV equals nRT, because you are the ideal student. Okay, now the ideal gas law does not solve for a mass. However, it does solve for moles, which can be easily, readily converted into a mass. So what we're going to do is rearrange this equation and solve for N. So I'm going to divide both sides by RT. And I'm going to get N is equal to PV over RT. Okay. All right, so I'm going to plug into this. So that is my goal, is to plug into this. I'm going to draw my line right over here. Okay, and the first thing that we do anytime that we use the ideal gas law is we plug in the ideal gas constant, and that is 0.0821 liters atmospheres divided by moles Kelvin. This tells me the units I need for all of everything else. Okay. All right. So what do we have here? we do have a volume, and the volume happens to be in the correct units of liters. So I'm going to plug that directly in, and that's 0.34 liters. Okay. We have a temperature right here, but that's not in the correct set of units. So what we're going to do is add 273.15 to that, and we're going to round it to 1 decimal. So hopefully that works out well for you. And that would be 352.6 Kelvin. And that's my temperature. And then I have a pressure, and it must be in the units of atmospheres, but it's in millimeters of mercury. So what we're going to do is we're going to convert this 692 millimeters of mercury into atmospheres. So that'll be 760 millimeters of mercury, 1 ATM. And this has 3 significant figures. This has infinite and infinite, so this will have 3 significant figures when I do that. And that atmosphere value will be 0.911 ATM. So that is going to go right here, 0.911 atmospheres. So what I have done is I have enabled myself to cancel out the atmospheres, to cancel out the liters, to cancel out the Kelvin, and I'm left with, in the denominator, 1 over moles. So that 1 over moles becomes moles because that's what N is. So the first thing I'm going to do is I'm going to plug this into my calculator using significant figures. This is 3 significant figures. We'll call that infinite. This is 4 significant figures, and this is 2 significant figures. So I'm going to have 2 significant figures for my answer. This is 0.911 times 0.34 divided by 0.0821 divided by 352.6. And that will be 1.1 times 10 to the negative 2 moles of CH2Cl2. Cool. That has 2 significant figures. Now, the question is, am I solving for what I want? And the answer is no. What I need to do is I need to solve for the mass. So I need to convert this value into a mass. So I'm going to scroll this up here just slightly, and you should be able to do this. This is 1.1 times 10 to the negative 2 moles of CH2Cl2. And I'm going to convert this into mass using my little bits of stoichiometry that I hopefully remember. Okay. And this will be 1 mole of the same formula, CH2Cl2. And then I'm going to need to determine the molar mass of CH2Cl2. So 12.011 plus 2 times 2 times 1.0079 times plus 35.453 times 2. And that molar mass is going to be 84.933 grams CH2Cl2 equals moles of that cancels out. And now I'm going to say 1.1 times 10 to the negative 2 times 84.933 divided by 1. This has 2 significant figures. This has 5 significant figures, and this has infinite number of significant figures. So I'm going to plug that into my calculator. 1.1 times 10 to the negative 2 times 84.933 divided by 1, and I'm going to get the correct number here in just a moment. Okay, and so that number is 0.93 units of grams, formula CH2Cl2. That has 2 significant figures. Leading zeros don't count. I'm going to zoom out on this just slightly so that you can see the vast majority of this problem. Let me zoom on out just a little bit more. And here we go. So you can see the whole problem here all at once. Okay, I used the ideal gas law, and I solved for moles and then converted the moles into grams, and I've got my number. So hopefully you enjoyed this a lot. I am the Crazy Hat Chemist, and watch me on YouTube. I love you all. I love chemistry, and I hope you have a fantastic day. I'll see you next time for the next video and the next YouTube. Talk to you later. Bye now.